I'm recording, and we are in production. So what's going on here? This is a lecture, actually a series of lectures. Let me show you.
Hi everyone.
It's a series of about 16 lectures, and that is supposed to teach us about practical zero knowledge. Practical zero knowledge means how we do zero knowledge in the real world. As I said before I started recording, I know zero knowledge as a theory, and I think I know it decently well. But I don't really understand how Snarks and Stark do their practical magic. I don't know exactly how they manage to make everything non-interactive, and I don't know how they manage to make it so efficient. So the purpose of this course is to start finding out. Now, I don't know if you know the names on the screen, but these are very, very high-profile names. Shafi Goldwasser. How many of you have ever heard of Shafi Goldwasser? So, Shafi Goldwasser is one of the co-inventors of zero knowledge in general. The invention of zero knowledge is usually attributed to a paper from 1985, which is a year before I was born, by Shafi Goldwasser and Silvio Micali and Richard Rakoff. Now, does the name Silvio Micali ring a bell to anyone? So, Silvio Micali, yeah, you went to the same elementary school with him. Okay. Silvio Micali then went and founded a project called Algorand, which I'm sure you've heard of. So we're talking about very high profile people. Dan Bonnet is also a forefather of cryptography, of modern cryptography. He, for example, a lot of people like to say that Shor's algorithm, quantum algorithm, can break modern encryptions, but it's not completely true. Yeah, Shor laid the foundation, but it was Dan Bonnet and his PhD advisor, Richard Lipton, that came out with the Bonnet-Lipton algorithm that actually attacks what is actually used in ECDSA signatures. And the rest of the people here are all are not forefathers, but like rising stars, while people like Shafi Goldwasser and Dan Bonnet went ahead and created tons of zero knowledge and reinvented the modern cryptography. These guys were busy being potty trained or not existing yet, and they're all rising stars of the last 20 years or so. I've run into their names several times, each and every one of them. So and those that I've heard talking, they gave a great lecture. So I think we're in for a very nice course, and with no further ado, let's begin. Today's lecture, we're privileged with Shafi Goldwasser, the mother of zero knowledge, going to tell us how she understands it, and it's in a broad view. And essentially we're going to watch it together, and if you have any questions, ask me, and I will pause. If I have any remarks, I will pause, and we're going to, it's like a guided watch, because I think these lectures are a bit too technical for a non-technical crowd, but with some guidance, I think there is a lot of value to be extracted. So with that, let Shafi have the stage.
Hi everyone. I'm giving the first lecture in the course on zero knowledge proofs, and my lecture will be an introduction to zero knowledge interactive proof.
Can you hear well as a start? A lot of reverb. The problem is that the video itself is a bit low quality. Okay, I think you're getting the echo from me. Let's keep trying.
And I'm very happy to be co-lecturing with Dan Bonnet.
Okay, you hear it double, so I'm just gonna put headphones and I think it will solve it.
Song, Justin Taylor, and Yu Peng Zhang. So we're talking about hi everyone, I'm giving the first lecture in the course on zero-knowledge proofs, and my lecture will be an introduction to zero-knowledge.
Is it better like this? Clean. Okay, great. So I'm starting from the top. So if you have questions, stop me. If I have comments, I will stop.
Hi everyone, I'm giving the first lecture in the course on zero-knowledge proofs, and my lecture will be an introduction to zero-knowledge interactive proof. And I'm very happy to be co-lecturing with Dan Bonnet, Don Song, Justin Taylor, and Yu Peng Zhang. So we're talking about proofs. Let's start with classical proofs. So when we think of a classical proof, we think about these very esteemed provers, Gauss, Euclid, A. McNoether, Alan Turing, and our own Steve Cook. And we think about theorems, the kind of theorems that you learn perhaps in geometry in class, where there's a bunch of axioms, there's a claim that you're trying to prove or a theorem. You make a sequence of derivations from the axioms, and then eventually you declare the theorem is proved. It could be the prime number theorem, the Pythagorean theorem, and so forth. But today we're going to think of proof as an interactive process where there is the prover, but maybe more importantly for our study, there is a verifier. So there is an explicit reference to whoever it is that's reading the proof and verifying it is correct. And we think about this as follows. There's a claim, which is an input to both prover and a verifier. Both of the prover and the verifier are actually algorithms. And the prover sends a string, which we will refer to in this slide as a proof. The verifier reads this. So if you would like to think about that geometric proof, the verifier is the teacher reading your proof, and at the end accepting is it correct or reject, accepting the claim as being proved or not. In fact, in computer science, we often talk about efficiently verifiable proofs or NP proofs. And those are proofs where the string that the prover sends to the verifier is short. And the verifier, in addition, doesn't have all the time in the world to read it. He has polynomial time. Now, to be more explicit, what does it mean by short? What do we mean by polynomial? What we mean is that the string that the prover sends to the verifier is of size polynomial in the length of the claim. So we think about the claim as string X, binary string. The message here is binary string W. The length of W is polynomial in the length of X. So if it takes 100 bits to describe the claim, W's length should be polynomial in 100.
For those of you who aren't sure what polynomial is, it essentially means to some power. It means like if the claim is of length 100 bits, then the proof can be 100 bits or 100 squared bit or 100 cubed or 100 to the 50, but it wouldn't be more. It wouldn't be like exponential. So polynomial is just the way computational theorists say reasonably small.
And the verifier's time is also polynomial in the length of X. So it could be linear, just the length of X, quadratic length of X squared, or the length of X even to 100, as long as it's a polynomial function. Again, the verifier is an algorithm. It takes as input both X, the claim, and W, the proof string, does some processing, and at the end decides whether to accept or reject. We often say either accept or 1 And when we say reject, it's either 0 or reject. I'll use those interchangeably. What are some examples? And these are going to be important examples for the duration of the class today. One example might be of an NP proof and a claim is that the prover is trying to convince the verifier that a particular number n is a product of two large primes. This is an...
Well, I don't know if you know this. They say that prime factorization is a hard problem. And prime factorization is essentially given a number and you want to find out what prime numbers you need to multiply to get that number. And people think that it's a hard problem, but there is a caveat because if one of the factors is small, like if I gave you a gazillion, bajillion times 5, then it's easy for me to find out 5 is a factor. And factoring is only hard when all the factors are large.
Interesting claim, because the verifying polynomial time, we don't know of a procedure for it to be able to convince himself that n is a product of two large primes. So we need the help of a prover, perhaps an all-powerful prover, certainly more powerful than polynomial time. Again, for this portion of the class, I don't pay any attention to how much time it took the prover to come up with a proof.
A good analogy here is that we can think of provers as miners and as verifiers as normal users. We don't mind that the miners have to work harder to create the proofs because only the miner or the proposer or whatever you call it needs to do it. It's like a large entity with the means to it. The entire point here is that we can have a serious project like a supercomputer or something do very hard work, but it's very easy for us, for each and every node in the network to verify it. So I think one example is the blockchain itself, which takes a very long time to create due to the difficulty, but verifying it is much faster.
All the attention that is going to be devoted to how much time it takes to verify a proof once it's sent. Later, we will dedicate our attention to the kind of claims that can be proved by a polynomial time prover who knows maybe some extra information, which enables it to convince the verifier of the correctness of the claim. So for now, let's go back to n is a product of two large prime. What's a proof? Since the prover's time might take a long time, we don't care about that. We just take attention to how much time it takes to verify. The prover just factors n. Let's say the two prime divisors are p and q, sends it over to the verifier. What does the verifier have to do? Is to multiply p times q and see that he gets n back. Multiplication is an easy operation, polynomial time. And he has to check the p and q each are both primes, and that's also an easy operation. We know how to do it in polynomial time. And if that's the case, he accepts, otherwise he rejects.
She just breezes over it, but actually we didn't know how to deterministically check for whether a number is prime or not. We had the Miller-Rabin algorithm, which is the one that is used in practice to this day, which is a probabilistic algorithm. And it's called the BPP algorithm, and we will see. I believe, I'm guessing that somewhere within this lecture, Shafi is going to define what BPP is, and then we'll talk about it some more. But the thing is that we know since the 80s how to check primality with an arbitrary small error, but only in, I think, 2012, Agrawal et al. Managed to find an actually deterministic algorithm that does it. Just a tidbit.
So after this interaction, what does the verifier really know? He knows the claim is true and is a product of two large primes. He knows something extra. He knows the primes themselves is actually more than was necessary in order to convince yourself that n is a product of two large primes. Or is it? Is there some other way to do that? We will see in a couple of slides that there is. But let's look at a few more examples. Second example. Now the prover is trying to convince the verifier that a number y is what we call a quadratic residue mod a modulus n. So the input to these two, prover and verifier, is a pair y and n. And the claim is y is a quadratic residue mod n. What does it mean to be a quadratic residue? It means that if you look at the equation, y is equal to x squared mod n, it's solvable. That is.
Okay, I'm guessing that a lot of you really lost her in this slide. Am I guessing right, or are you all, or is this technical level comfortable for you? Because I think this is a point where I would like to stop and break down, but I'm still feeling the audience. So please let me know. Would you like me to explain this, like break it down a bit more? Okay, so if you're comfortable, I'm gonna keep going.
There exists an x, and it's an x that's actually essentially between 1 and n, and furthermore, it's what we call relatively prime to n, so there's no divisors in common between n and x. That's a solution to this equation. So there is an x such that y is equal to x squared mod n. And what would be the proof of that? Well, maybe the verifier can do it himself. It turns out that this is a very hard problem. So it's hard, for example, to find the square root of y mod n. Because if it was easy in polynomial time, the verifier wouldn't need the prover. How hard is it? It's as hard as factoring n, a well-known hard problem for classical computers. But the prover, as we said, he's all powerful, or she in this case. So she finds out an x, sends it over to the verifier
Yeah, okay, so some people asked, okay, is there a problem with the voice, with my voice or the YouTube audio? Okay, too bad. Yeah, we'll try to fix it in a second, but before that, I wanted to say something about all this quadratic residuosity thing, because okay, so what is the deal with this quadratic residuosity? So she wrote the equation x squared is congruent, sorry, y mod n. What does this mean? So when we say mod n, you want to think about it a bit like a clock. You know, if the time right now is 10 o'clock, and then you wait for 4 hours, then the time would be 2 o'clock, right? And if you'll wait for 14 hours, the time would still be 2 o'clock. And the thing is that it repeats itself every 12 hours. So when you are doing time arithmetic or hours arithmetic in your head, you're actually working modulo 12. So what you're actually doing, if right now the time is 10 and you want to know what's the time in 4 hours, one way to describe it would be that you take 10 and add 4 to get 14, and then you divide by 12 and look at the remainder. Okay? So when we are talking about mod n, so when we say x squared equals y mod n, what we're actually saying is essentially that, okay, I wrote it twice. It just means, or let's go before that. When we say that A is equivalent to B mod n, we are just saying that n divides B minus A. So for example, if we the hours, I don't know, 1 a.m. and 1 p.m., which is equal to 13 look the same on the clock because 12 divides 13 minus 1, right? So this is the thing. And when we are saying x equals y mod n, it's essentially saying we are asking ourselves, we are given a number called y, and we are asking ourselves, is there a number x that we can square and then just divide it by n and look at the remainder and get y? So like a practical example is, like a simple example would be, is there an x such that x squared is equivalent, is congruent to 6 mod 10? And the answer is yes, because we can take x equals 6, then x squared equals 36, right? But we want to look at it mod 10. So if we take 36 and divide it by 10 and look at the remainder, think of it as like a clock with 10 hours that you went 36 hours and then see where you landed. And so this thing is equivalent to 6 mod 10. So then we get, okay, 6. There is a number that we can take the square and then just look at the remainder, just look where it is on the 10 hours clock, and to get the 6 that we wanted. And so a mathematician would say, would describe this as 6 is a quadratic residue mod 10. This is what, when we say this bombastic number, it just means there is a number that we can square, and then divide by 10 and take the remainder, and we get 6. And then I'll leave you with an exercise, just for the heck of it. 4 is not a quadratic residue mod 10. And to do that, you just need to take all of the numbers between 0 and 9 and square them, and look at the remainder dividing by 10 and see that you never get a 6. Okay, so I leave it to you to verify, but all of this notation is a very simple notation for a very simple concept. Usually we take n to be very, very large, by the way, which is why we can't solve this by trying each number. The entire point is that n would be exponentially large.
Squares mod n, compares to see if it's equal to y, and if so, it accepts, else it rejects. Again, it's an NP proof. There's a short string, x, that will convince the verifier to accept when the claim is correct. What happens after this interaction? The verifier is convinced that indeed there exists an x such a y is equal to x squared mod n, but he also knows x. He knows the square root of y. Last example before we start defining this more generally. Here, the claim doesn't talk about numbers. He talks about graphs. There are two graphs. Turns out, if you look more carefully in these two graphs.
When a computer scientist says graphs, it doesn't mean like a graph of a function like you know from high school and this kind of stuff. It's just a bunch of dots called vertices or nodes connected by lines called edges. Like the information captured in a graph is that you have like a few data points and the affinity, some relation between them. For example, you could draw a dot for each person on Facebook and draw a line between two people if they are friends. And I am intentionally saying Facebook and not Twitter, because on Twitter, it's not a reciprocal thing. You can follow someone, but it doesn't mean that they follow you. In Facebook, either you're friends mutually or none, or you're not friends. There isn't like a directionality to it, which is why it's described by this kind of graph.
They are actually isomorphic to each other. In plain English, that means they are the same graph but drawn a little differently. And formally, it means that there's a mapping from the vertices on the graph on the left to the vertices of the graph on the right, so that if you take this mapping, which we call the isomorphism, pi, from numbers 1 up to 10 on the left to numbers 1 up to 10 on the right, or vertices from the left to the right, it will be the case that essentially the one on the left, if you map it to with the isomorphism to a vertex on the right, let's think of it as 1. Similarly, the 2 on the left to the 2 on the right, if there's an edge between the 1 and 2 on the left, there's also going to be an edge between the vertices that these two are mapped to on the right.
Okay, another way to see it, which I think is a bit more friendly to the non-technical watcher, is that we want to show that we can get from this graph to this graph by just moving points around. And so what we will see is if we'll take this point and move it to here, we'll take this point and move it to here, and we go according to the numbering, then we will see that the lines in this drawing will align the lines in this drawing. Now, I also want to go over the notation because I think a lot of people are a bit intimidated by mathematical notation, but it's very comfortable and compact when it's easy to, when you are used to it, much more than using words a lot of the time. And because you can condense a lot of information into very little text. And so this pi here is just a rule. It's a rule. It's given a number between 1 and 10, and it spits out a number back. And this rule, we wanted to show that this is an isomorphism, that it shows that these graphs are essentially the same. So what does it mean? First of all, it means that it's what we call a bijection. It means that if I give it two different numbers, like 6 and 10, I'm going to get two different numbers out of it. But what's more important, that if I look at two numbers and see there is a line between them, and then I look at here at the same two numbers, there will also be a line between. See, like here there is no line between 3 and 9, and here there is no line between 3 and 9. Here there is a line between 7 and 5, and here there is no line between 7 and 5, because I think she made a mistake. Yeah, I think there is a slight mistake on this slide, maybe. And thank you, Shafi, for embarrassing me. But or maybe there isn't. No, maybe the point is that, yeah, I don't want to look at 1, 2 here and 1, 2 here. I want to look at 1, 2 here and like the numbers that 1 and 2 are mapped to over here. So we'll see. I think maybe there is a bit of a mistake in this slide.
And that's true for every pair of vertices. That means that these two graphs are isomorphic to each other and that pi is an isomorphism. So how hard it is to describe how long is pi? Is it polynomial size and the size of the graph? Yeah. Essentially, it assigns for every vertex a name on the other graph. And that's just, essentially, if there are n vertices, it's length n. And how much time does it take the verifier to check it? He has to go for every pair of vertices on the left, check if there is an edge between them on the left. There's also an edge between where they were mapped on the right. And if there's no edge between them on the left, there should be no edge between them on the right. After the interaction, the verifier will believe that two graphs are isomorphic if he got a good isomorphism, but he also knows an isomorphism. So all of these examples are examples of NP proofs. Now, of course, we are not interested in a particular number n or particular number y or particular pairs of graphs. We're interested in the problem more generally, and we call this a language. That is all the n's which are product of two primes. That's the language of composite numbers, which are product of two primes, or all the y's in n pairs, such that y is the quadratic residue mod n. In other words,
yeah, let's unpack it a little bit. The thing is that everything in the world can be described as a binary string. And because if I can describe it with words, with language, then I can decode every letter and every punctuation and every white space into, not decode, encode, into like a binary code or something. The point is that binary strings are not restrictive in any way. They're just a simple representation. You can use any other alphabet if you want. It doesn't have to be zeros and ones. The point is that you can take a subset of strings, and language is just that. Like you say, okay, I have what is a valid encoding of a number, and then I want to look at all the strings that represent numbers that are the product of two large primes. Now, I need to explain exactly what large is, but I'm going to ignore it. But the point is that now we can ask, okay, if we are given a string that is a number, can we verify if it's the language in the language or not? Can we know if it's the product of two large primes or that it has more factors, or maybe, well, we can check if it is prime itself, but like, can we tell apart a product of two large primes from a product of three large primes? And that's a good question. But the question here is not if we can tell them apart, but if someone all-powerful can show us a proof that will convince us.
we're interested in languages. Formally, a language is just a set of binary strings X that satisfy some property. And an NP language is defined to be, this goes back to Cook and NP completeness, is defined to be those sets of strings, L, is an NP language if there is some verifier, V, who runs in polynomial time, polynomial in the length of the X, such that both two conditions hold, and that is completeness and soundness. What does it mean that completeness holds? It means that when X is in the language, if you're talking about a claim, or in the example, let's say of composite numbers, when the language.
I usually like to say it as a slogan. Completeness means that I can convince you of facts, and soundness means that I can't convince you of counterfacts. I can only convince you of things that are completeness means that I can convince you of everything factual, and soundness means that I can't convince you anything counterfactual. Now, again, I want to unpack the notation a little bit. I also want to say that I hardly get any comments and questions. So don't be embarrassed. Like before I asked if something is clear and then someone said it isn't, I'd wish for you to say it in advance. The entire point here is to make this approachable for as many people as possible. I do want to unpack what's going on here a little bit. So as I said, poly, when we have a string X and we put these two lines over it, it just means the length of the string. Now, this poly here essentially means it could be any polynomial function. It could be like to square whatever you put inside, or to cube, or whatever you can think about. We are not talking about a specific function. We're just saying there is a polynomial, and right now we don't terribly care what it is. And now the completeness says that if the string is in the language, if X represents a product of two primes, then there is a witness that will convince us of it. So this funny notation is just 0 and 1 means just this thing, just means the set of 0 and 1. It's like either 0 or 1, we usually call it a bit. And the string here, the star here means that we are allowing ourselves to make like a string of any finite length. It could be a single bit, it could be 100 bits, it could be anything. And V, just remind that we said in advance, we also said it here, this is like an algorithm which is polynomial, which is reasonably fast. And the completeness says that if something is in the language, then there is a witness that could be technically computed with enough work, but usually far too much work for a normal computer, and that would convince the verifier, again, like D prime factorization. And soundness means that if X is not in the language, then no matter what proof I provide to the verifier, he's going to say, no, that's not a good proof. Because there aren't any 2' numbers that I can multiply to get the number, for example.
Language is a language of composite numbers which are product of 2 primes, and we're given such an n, then there has to be a polylog proof or witness W. The prover can send to the verifier such that the verifier examining X and W will accept. So, but completeness is not enough. We also need soundness, and that is to make absolutely sure that when X is not in the language, for this example, n is not a product of 2 primes, then there is no witness that will convince the verifier to accept. In other words, for all strings W that the prover may send to the verifier will reject. So we usually talk about completeness allows honest provers to convince the verifier. Soundness ensures that regardless of what a cheating prover is trying to do, he will not be able to convince you the correctness of an incorrect claim. But our question in this course is not about NP or NP completeness, but rather we're asking, is there some other way to prove these type of theorems? Can a prover, for example, convince a verifier that Y is a quadratic residue mod n without sending a square root? So this is the question that motivated Silva Mikali, Charlie Rakoff, and myself to study zero-knowledge proofs in the early 80s. And this is a process that took about 3 years. The answer is yes. And the main idea, even without getting into the mathematics, is the way that the prover will convince the verifier that the claim is true without giving away the NP proof. In the example of the Y is a quadratic residue mod n, without giving the square root, is to prove instead that I could prove it if I felt like it. So I'm not going to prove it to you, but I will prove that I could prove it. And somehow being able to prove that I could will imply that at the end, the verifier will be convinced, and yet he will not know a square root, he will not know the factors of n, he will not know an isomorphism. In fact, he will get zero knowledge in addition to the fact that he claim is true. Of course, we will need to define what it means to be zero knowledge precisely. So before we define it, I want to give you an idea of how possibly you can prove that something is a square root or the two graphs are isomorphic and so forth without actually giving the isomorphism or giving the square root. And I'm going to start just letting you know that this is no longer going to be a prover sending a string W to a verifier. We're going to need to change the proof model. We're going to need 2 new ingredients. One of them is going to be interaction. Rather than the verifier just passively reading the proof, he's going to have to be engaged in a non-trivial interaction with the prover. So like you see in this picture, there'll be messages going back and forth. Prover sending a message to the verifier answers back and forth, back and forth. It might be 3 steps, it might be 2 steps, it might be length of X steps, but it will be polynomial number of steps. It will be more than a single message from prover to verifier. Later on in this class, we will see that there is a way to remove much of this interaction. There will still be, in a sense, at least a single message from prover to the verifier and some preliminary stage. But for now, we have interaction. Interaction is not enough. We also have randomness. What do we mean by that? We mean that the verifier is not just going to be a deterministic algorithm evaluating what he received from the prover. He's actually going to be allowed to toss coins as a primitive operation. And his questions to the prover will depend on the result of tossing these coins. Another way to say that is that his questions are somewhat unpredictable. Because if they were all predictable, the prover could have anticipated them and just sent him the one string W in advance. But since they are unpredictable, after the prover sends a message, the verifier may ask, depending on his coin tosses, many different options. And the prover is supposed to be able to respond to all of them. What is inherent in the fact that the verifier tosses randomness is that we're also going to be willing to accept a small probability of error. What does that mean? We will get to the formal definition in a few minutes. Informally, what that will mean is that whereas in geometry class, when you gave the teacher a proof, they checked it, and it was supposed to be 100% correct. We are going to have, as a formal part of the model, allow a small probability of error, but it's going to be quantified, and you're going to have to be able to show that your error is smaller than 1 over, I don't know, Avogadro's number, or a negligible error. We'll get to that in a minute. For now, the proof model is changing. It's interactive. It's probabilistic, meaning the verifier can toss coins. That means that there's a lot of possible interactions that will come up between prover and verifier.
Yeah, okay. I think maybe we need to be a little more astonished by the philosophical implications of the movie, because zero knowledge is just a technique. It starts with the realization that the whole concept of proving someone that something is true is a lot more involved than just writing a proof. And in fact, in some case, we can decouple proving that there is a solution with proving that I know the solution. And so maybe she'll talk about it. It's called like a proof of knowledge, which is more than just zero knowledge. And essentially we can talk about, we can just separate knowing that something is true and knowing the solution. And I think a very nice example is the question, does this number have a prime decomposition? Given a number, can I write it as a product of prime numbers? Now, we know, like Euclid proved 3,000 years ago, that any number can be written as a product of prime numbers. And we studied it at school. And so essentially, if you ask me whether this number can be factored, and I always just say yes, I'm a stupid prover that just says yes all of the time, then I will always be correct because it's just true trivially for any number. But it is zero knowledge in the sense that you don't learn anything from my answer, even though we have soundness and completeness, but the soundness is trivial because the answer is always yes. And this kind of, I think it's a very extreme example of the difference between proving that something is true and proving that I know the answer. And we can ask ourselves, can I prove to you that something is a quadratic residue without me even knowing what the root is? So that would be an example of a zero knowledge protocol, which is not a proof of knowledge.
So there are a lot of possible executions. It's still going to be the case. They both get input, which is the claim. And at the end of this question answer period, the verifier will take the history of the interaction, the coin tosses that he's made, run an algorithm, and decide whether to accept or reject. Let's look at the first example. The first example is not going to even be mathematical, but it will be something from sort of the physical world. The claim here will be that this particular page right in front of us has two colors rather than a single monochromatic color. And the scenario that I would like you to keep in mind is, let's say the prover can tell colors apart, but the verifier is colorblind. And the prover is trying to convince the verifier that this particular page has two colors. He's not going to enable him to see colors for the future. So in some sense, all he's going to convince him is that this page is two colors and nothing else. So in that sense, it will not be transferring to him anything beyond the claim. How? So here's the first step. The first step is the verifier uses his coin, flips a coin, and with the following idea. If the coin lands on heads, he takes the page and flips it over. And if it lands on tails, it doesn't change the page at all. Let's assume that he tossed the coin, and indeed it was heads. So he flipped the pages so that what earlier was purple in the top, now it's on the bottom. And now he does this in the privacy of his own home, not showing the prover the results of his coin. But what he does is he sends the page over to the prover. The prover now looks at this page. He knew what the page looked like before, and he now sees what the page looks like now. Since the prover can distinguish colors, he can tell whether the coin landed on heads or tails, right? And indeed, that's exactly what he says. He checks whether the page was flipped or not. He writes the value of the new coin prime, to be heads if it's flipped, tails otherwise, then he sends back coin prime. He says, listen, I think you tossed coin prime. The verifier, the rule right now is that the verifier, if indeed the coin that the verifier tossed is equal to the coin prime that the prover thinks he tossed, he says, well, it looks like the prover could tell whether the page was flipped or not. But he couldn't tell if it was only a monochromatic, so there must be two colors on this page. I accept the claim is true. Of course, if the coin that is sent over is different than what he flipped, he says, well, he couldn't even tell that it flipped it. There's certainly not two colors there. I reject.
So did everyone follow this story? I think it's a very, very, very good example for understanding the broad story of how many zero knowledge proofs works. Essentially, imagine that there is a page, and the page looks like a blank page to you. And then someone comes and tells you, well, I'm a superior being to you, and I can actually see two colors here. You're just so inferior that you can't tell them apart. And you say, oh, really? So you turn around, and then you flip the page so many times that the guy can't really see how many times you flip it, and then you show it to him and ask him, okay, if you're so wise, can you tell me if I flipped the page or not? And if they can tell you, then it means that there is an information there that you can't see. But if they can't, then it means that they are bluffing, and essentially for them it's also a completely blank page. So the thing is that they don't tell you any information about the drawing that they see. Like, you learn that they can see something on the page that you can't, that can tell them whether you flipped the page or not, but you don't learn anything about how it looks. It could be a square, it could be a circle, it could be a dragon. You don't know. You got zero knowledge from the protocol. That's the entire point.
Let's try to analyze this for a minute. Clearly, if there are two colors and the prover follows this procedure, then the verifier will always accept, because the coin prime will always equal the coin. If there's a single color, the prover cannot tell whether he flipped or not. He can still try to guess, he's a cheating prover, whether the coin landed on heads or tails. And he has a 50-50 chance of guessing correctly. So the probability that he sends the correct coin is a half at most. And if the verifier accepts in this case, the probability the verifier accepts incorrectly, because the prover was lucky, but there's a single color on this page, is...
Just a second, sorry. Need to do something. Okay, we're back.
1/2. So if there are two colors, you will always accept. If there's a single color, the probability accepts is less than a half. There's a gap between them, but you may not like these odds. Say, what? I'm going to accept incorrect statements, claims, with probability of half? No worries. You can repeat this process again and again. Each time the verifier tosses a new coin, decides whether to flip or not, sends the result, and so forth. And now, what is the chance that the prover, in case there is only a single color, so it's not correct claim, he's able to provide the verifier each time with a correct coin he tossed? It's 1/2 the first time. It's 1/4 to be able to do this twice in a row. It's 1/8 to do this 3 times in a row, and it's 1 in 2 to the k if you repeat this k times. So the probability that the verifier will accept after k iterations of this is very, very small. So what has happened here? I was able to convince a colorblind verifier of whether a page has two colors or not, so that he always will accept when there are 2 pages, and he will accept that there's 2 pages incorrectly with extremely small probability. Let's see this again, this idea, a little bit different, of using interaction and randomness to be able to convince someone of, this time, a mathematical statement without transferring sort of the obvious NP proof over. So the next example is the example that we started with, and that is the input to the proven verifier is a pair n and y such that there exists an x such that y is equal to x squared mod n. Or is it the prover is trying to convince the verifier that indeed this pair ny is a member of this language, the QR language, the quadratic residues language, those y's such that y equals to x squared mod n for some x. How would you convince the verifier of this case without giving him square root? Here how it goes. The prover as a first step chooses a random value 1r between 1 and n. In fact, to be absolutely correct, this r is supposed to be between r and n and have a greatest common divisor with n, which is 1, meaning there's no common divisors between r and n. For those who don't want to really dwell into this, let's just think of it as a random number between 1 and n.
Yeah, just if you want to know, GCD means greatest common divisor. It's the largest number that divides both. So, for example, the GCD of 6 and 4 is 2. So if n is 6, then r equals 4 would be a bad choice because there is a number larger than 1 that divides them both. When saying that two numbers have GCD 1, the word we usually use for it is disjoint. What she's asking for here is that R and N are what we call disjoint numbers. And it essentially means, you know, that we can break R into primes and we can break N into primes, but they would be different primes. And there is no prime number, which means there isn't any number other than 1 that divides both of these. It's really not that important, as she said, but if you want to know what this means, this is what this means.
And then what he sends to the verifier is r squared. He doesn't send r, he sends r squared, and let's call it s. Sends up s. And he says to him, listen, if I gave you both square root of s and square root of s times y, where y is the input, then you would be convinced that the claim is true. Because if s has a square root and s times y has a square root, then also y itself has a square root, mod n. But if I did that...
Okay, I think this is a good time to run this protocol on a small example ourselves, because it might be a bit abstract like this. So let's do this. Okay, so let's do a small example of ZK protocol for quadratic residuicity QR. Yes, not gonna bother going through the pain of spelling this word. Okay, so say I want. Okay, so let's go with n equals 1,000. So if I take I don't know, x equals 87, then I get that x squared equals, so how much is 87 squared? I need to check it for a second. Excuse me. Is equals 7569. Okay, let's not go with 1,000 even. Let's go here with a more difficult number. Okay. I want a prime. I think this is a prime. Yeah. And so so if I divide this by 697, Okay. Okay, so this thing is actually 697 times 10 plus 599. Or in other words, I know that 599 is a quadratic residue because I know that 87 squared equals 599 mod 967, right? Because if I take 87 and square it, I get this number. And if I divide it by 697 and take the remainder, I get 599. That's cool. But how can I convince you of that without... Oh, okay, yeah, sorry. I'm dyslexic. I have a learning disability. This is what should be here. Because on the calculator, I kept in 697 instead of 967. Thanks, Yuval. Okay, how do I convince you of that without telling you X? So as we said, let's go with her notation. So I choose a random number. Let's say 93. Okay, and send it to you. Okay, now what did she say there? She said there that I don't send it to you. I just want to follow her notations. Okay, R equals 93. I compute S equals R squared mod N, which means 93 squared mod 697, and which obviously I'm gonna check my calculator for me. Which is 285. Okay, and then I send 285 to you. Okay, so say that, and just a second, say that, so the thing is that then S is a square, right? I know that S or 285 is a square mod 697, right? Because if I square it, then I get this. If I square 93, I get 285. And I know I can also take S times X, S times, sorry, Y, what she called the X squared, which is just, so it's 599 times, or C dot, 285, which is 12. I'm gonna stop writing mod at this point, but it's 12. 647. The numbers don't matter this much. But the point is that SC dot Y also has a square root. It's the product of roots, right? Because if S equals R squared and S and Y equals X squared, then SY equals SY squared equals just I didn't want to write. Sorry, SY equals R squared times X squared, which is that R times X squared. This is just like grade school math. Also, it's under the hood, it's modulo, but I'm kind of ignoring this. So to check that y is indeed a square root, square, I need to convince you. Or let's remain with this number. If we know that, convince you that 599 is indeed a square mod 697, I need to convince you that I know a square root of both 599, oh no, sorry, of both 647 and 285. Why? Because then you know that this number is a square, and the product of this number with our original number is also a square, which must mean that this number is also a square. What is the problem here? The problem is that if I show you the squares of both of these numbers, then you can compute back this, right? Because you compute y. Because if you know that if you know s and you know the square root of s, and I tell you the square root of sy, then from this information together you can piece together y, right? Or square roots of r, sorry. So I need to somehow convince you by only telling you the square root of one of these numbers. So how do we do that? The idea is that, again, if I can show you that this and this both have a square root, then it would imply that this has a square root. So the only situation where I'm trying to cheat you is if at least one of these two numbers doesn't have a square root. Because again, if they do have a square root, it immediately implies that, that this number also has a square root. So it means that at least one of the two numbers doesn't have a square root. So if you flip a coin and ask me to give you the square root of one of these numbers, there is a probability have that you're going to fall on a number for which I can't provide you a proof. So no matter how I answer, you would check my answer and you would see that it's wrong. So this is essentially the idea here.
That's like sending you a square root of s would be r, square root of s times y would be r times x. Then you would know a square root of y, right? You would know x, just take r times x divided by r. And the whole point here is I don't want to give you both. So what I'm going to do is I'm only going to give you either square root of s or square root of s times y. But I want to convince you that I could have given you both square roots. And the way I convince it to you is I tell you, you get to choose You can choose to get a square root of s or square root of s times y, your choice. And I will be able to answer either question, but I'm only going to answer one. Now, if the verifier is smart, the way to choose which he wants is going to be to flip a coin, not to decide this deterministically, but flip a coin. So then with 50-50 chance, he will, in case the prover is cheating, ask for an equation that the prover cannot solve. Why? Because if the prover is cheating, he cannot solve both finding a square root of s and a square root of s times y, because in that case, he's not cheating. So the fact that he could do both means he's not cheating. I will flip a coin as a verifier to choose a challenge. Hey, give me square root of s, or hey, give me square root of s times y. He's supposed to do that. So if my coin turned out heads or one, the prover is supposed to give back the square root of s, which is r. And if the coin was tails, he's supposed to give the square root of s times y, which is r times the square root of y, or r times x. That's the square root of y. The verifier checks that he got the right answer. So he will accept only if indeed, when he takes what he got back and squares it, he will get back an answer for what he asked for. So if it was heads, he asked for square root of s. That in that case, it's s times y to the 0, just s. And if he asks for tails, he wants the square root of s times y. Let's analyze this. Again, if the claim is true and the prover acts according to the protocol, the verifier will always accept, because the prover can always give a square root of s and a square root of s times y. Again, the prover is all powerful. He knows the square root of y. He can, because he's all powerful. In fact, that's the only thing he needs to know. But what happens when the claim is false? Soundness is always the thing that's harder to show. If the claim is false, okay, then no matter what the prover does, the probability that he will be able to solve both equations, he can't solve both equations, he can solve one of them. So what's the probability I asked him to solve the equation that he knows how to solve? It's at most a half. Again, maybe a half is not enough for you. Repeat this 100 times. And the probability that the verifier can 100 times be so unlucky as to choose exactly the equation the prover can solve and not the other one which he cannot solve, in the case where the claim is false, is going to be vanishing with a number of trials.
Maybe we should stress it because she didn't say it explicitly, but in each repetition you need fresh randomness, which means essentially that in each repetition you are choosing a different R. This choose random R, you resample it every repetition. Otherwise, this obviously won't work.
1/2 if you try once, 1/4 if you try twice, 1/8 if you try third time, and 1 into the 100 if you go 100 times. And if you want it to go k times, it's 1 into the k. So what happened here? I can convince the verifier to accept when the claim is true. It's very, very unlikely I will convince the verifier to accept when the claim is false. And I never, if you think about it, transferred the square root of x, because every time I just give him a random r, which is the square root of s, or a random r times, the original x, or the square root of y. Random times the square root of y is random when you reduce it mod n. So it gives, essentially I'm sending him random numbers which are independent of each other, even if I repeat this 100 times, because each time I start again with a verifier, with a prover choosing a new r. So what made this possible? Here's one intuition. There's lots of possible executions. So there's lots of possible interactions or proofs. And the prover essentially chooses one of those many possibilities in the first step. When he sends r squared, he's sort of choosing one of these many possibilities at random. And every proof of these many random proofs is made of exactly two parts. One part is when I ask to see the square root of s, and one part is when I ask to see the square root of s times y. Seeing either square root of s or the square root of s times y gives nothing. If the verifier could have seen both, it would imply 100% correct.
And the reason it gives nothing is essentially this randomness. Because s is very random, then s times y is also very random. So that's why its square root doesn't tell you anything about the square root of the original y.
Yes. And the verifier chose at random which of these halves he wants to see, the square root of s or the square root of s times y. The ability of the prover, in principle, to provide either part or convinces the verifier that the prover could have answered both, and therefore the claim is correct. That's defined as precisely. All right. So we have P and V, and they are an interactive proof for a language, for a set of statements. If, again, V is polynomial time, but this time probabilistic polynomial time, and there's completeness and soundness. If the claim is true or X is a member of the language, the verifier will always accept. And soundness now has been modified. If X is not true, the claim is incorrect, or X is not a member of the language, then for all cheating prover strategy, no matter how hard they worked, the verifier will not accept except with negligible probability, like the 1 in 2 to the 100, or 1 in 2 to the k, 1 in 2 to the length of x. Let's introduce a little bit of notation. So this is a cheating prover. Every cheating prover strategy will only help the prover to convince the verifier with negligible probability. So a bit of notation. We use the following notation. We talk about the probability that PV, so open paren, PV, close paren on X, except in the case of X equal to L, X is in L, completeness is probability 1. And in the soundness case, we say that for all cheating provers P star, the probability that P star interacting with V on input X, the probability that accepts is negligible. What's a negligible function of length of X? That's a function that grows slowly than any 1 over polynomial.
Don't concern yourself too much with what negligible is. In most cases, not all, but most, negligible would be exponentially small. It would be something like half to the power of lambda or something like that. It would be just negligible is just very, very small. You really don't need to care about this vanishes faster than any other polynomial, this like inverse polynomial kind of stuff.
1 in 2 to the length of X is an exponentially small function, so it's smaller than 1 over polynomial for any polynomial. Interestingly, if you step back and you think to yourself, is this reasonable to call this an interactive proof? I claim that this is ultimately what a proof is. It should convince the verifier of correct theorems, and it should not convince him of incorrect theorems. If you only are managing to convince him with a probability that is so small that in the lifetime of the universe, it's not going to happen, it's good enough for me. And that is ultimately what a proof should be. It should convince you of correct theorems and not convince you of incorrect theorems. And an event that will take time in Avogadro's number, 1 in the lifetime of the universe, of convincing of an incorrect theorem essentially never happens. All right. By the way, interestingly, is that when you have an exercise, a homework, and you're coming up with an interactive proof, sometimes it's going to take a lot of work to get you to have verify always accept correct theorems and not accept correct theorems with negligible incorrect and accept incorrect theorems with negligible probability. You don't have to work that hard. You just have to show that completeness holds with probability C, and soundness does not hold, at most holds with probability S for C and S, which are a polynomial.
Yeah, it's a technique called amplification. And the point essentially is that we can look at the completeness and the soundness, and we say we don't need the completeness to be perfect. We don't need the soundness to be perfect. We just need them to be sufficiently far apart. Like if there is a probability, if for any word in the language, I will accept with probability at least 2/3, but for every word outside the language, no matter how the prover is trying to cheat, I will accept with probability at most half, then it's enough. Then we can repeat the entire thing many times and assume that if we catch them lying even once, then it's all over for them. then completeness will increase very much and soundness will decrease very much, and it will happen exponentially fast.
Part. So this will be equivalent to achieving probability 1 for C and negligible for S. This can be shown in some standard technique of using repetitions. So we define what an interactive proof of a language is. We also can talk about the class of all languages that have interactive proofs. And in the same way that we talk about NP as being all those languages for which there is an NP proof, we will talk about IP as all those languages for which there is an.
Okay, this is again a very interesting philosophical question. Essentially, I can prove stuff to you by writing a proof on a piece of paper and giving it to you. And I can prove stuff to you this way, that we have this interaction and you give me some random questions and I ask you and I give you answers. And the question is, am I more convincing one way or the other? So one way is trivial. Like if I can convince you by giving you just a proof on a piece of paper, then I can also do an interactive proof where the only thing I do is send you one message with whatever I would have written on this piece of paper. But is there more? Is there stuff that I can prove to you using this kind of protocol that I can't prove to you just with giving you a proof on a piece of paper, even if I'm all powerful and can do all the computations in the world? So this question can be written is IP strictly larger than NP?
Interactive proof. Again, the proof of runtime might be very slow, but the verifier has to be polynomial time, probabilistic polynomial time. All right. We have defined what an interactive proof is. But what about zero knowledge? How do we define zero knowledge? What is even the intuition of what should be zero knowledge? So here's the intuition. I want a zero knowledge interactive proof to be the kind of proof such that whenever the statement is true, then the verifier goes through a proof, interactive proof with the prover. And at the end, he's convinced with high probability that the claim is true. But in addition to that, he has a history of interaction. He has the coins that he's tossed. Maybe you've given him so much during this interactive proof that now he can compute a lot more than he could compute before. So for the example of the n, proving that n is a product of two primes, perhaps after the interactive proof, he can factor a number or compute a square root or find an isomorphism. We will say that the interaction was zero knowledge if what the verifier can compute after the interaction is essentially the same of what he could have computed before. Namely, the interaction has not increased the computational power or allowed the verifier to compute more than he could have computed before. Furthermore, we want this to be true, not just for the honest verifier who follows the protocol, but for any verifier, even a devious, malicious adversary.
It's the reversal here. First, we were worried about malicious prover, because the maliciousness of the prover is not about zero knowledge, because zero knowledge protects the prover from the verifier. So the soundness and completeness properties protect the verifier from the prover. It essentially means that prover can't prove falsities. Now the zero knowledge it goes the other way around. Now it's the verifier, the prover, who's concerned that the verifier can play dirty and somehow extract from him this information that they don't want to give away. Somehow they can play with the protocol in a way that coerces the prover to reveal the information that was not supposed to be revealed. It was supposed to be hidden. So this, in the previous properties, we talked about an honest verifier against a prover that tries to lie to him. And now we are talking that an honest prover, we are looking at an honest prover who's afraid of a malicious verifier who tries to extract and coerce information. So this is a bit of what makes this difficult, that you need to consider what each side is trying to do from the other, what each side should be protected from. you can't work in a setting where both of them are malicious, because as soon as nobody follows the protocol, you can't prove anything. So there is always a side that follows it and a side that tries to deviate. So when we talk about protecting the verifier, we assume that the verifier is honest and the prover is malicious, and now we are doing the other way around.
Adversarial verifier. This is slide is intuition. How do we mathematically capture this? Let's try. Again, we're going to do this slowly. So first of all, I want to say that this verifier has some sort of view, and I want to, so he's learned that after the interaction that a theorem is true with high probability, but he's also gotten a view. And that's the transcript, the answers and questions, plus the coins he tossed. We will define this formal variable, which is view sub v of pv on x, and that is a random variable. What I mean by that is that there's a lot of possible values that this variable can get, and this is a probability if they're distributed over the coins that v and p both tossed. Remember?
Yeah, okay, so let me just demystify the jargon here. And this thing, it's not a deterministic value. It kind of describes all of the possible values, where we are looking about all of the conversations that these two guys could have. This is what is called a transcript. Essentially, it's just a log of every single thing that every one of them said to the other. And this conversation could have many different logs, right? Because it depends on randomness used by the verifier and on randomness used by the prover and all sorts of other stuff. So this thing kind of says, okay, here is all of the possible options, and for each one of them, here is the probability that this particular option happened.
Remember, let's say in the example of showing that y is a quadratic residue, the prover tossed coins to select r. The verifier tossed coin to select whether he wants to see the square root of r squared or the square root of r squared times y. So those are all possible executions. These are all possible assignments that this variable can get. Okay, so this is the verifier's view. I will say that this view gives the verifier nothing new if the following is true. And this is called the simulation paradigm. This is the simulation paradigm has started with the concept of zero knowledge. It's used all over cryptography today.
This is a hard definition. I want to say in advance, this is probably the hardest thing to understand about zero knowledge, is this simulation thing. It's kind of weird. I think the way I get it intuitively is that if we know that these transcripts, they're like all of these conversations that we could have had, is something that we can very closely do for ourselves, then it essentially means that looking at the conversation doesn't tell me anything except what I wanted to know. Like there is no information concealed in anything that could have been said, except for what is guaranteed by the completeness and soundness, which is like being or not being in the language, being or not being a quadratic residue, being or not being a paper with two different colors on it, but for humans they seem like the same color. So the completeness and soundness gives us this bit of information, but the fact that I don't really need the prover to create a random conversation that looks as though I had a conversation with the prover means that the conversation itself doesn't have any excess information, in particular information that could be used to learn something about the answer that is supposed to be concealed.
What is the simulation paradigm idea? We say that the real view, so if we look at this blurb, or this great blurb that I call real view, which is essentially, this is a probability distribution. The points in this space are all the possible histories of interactions between prover and verifier plus the verifier's coin. I say that this view gives the verifier nothing new if he could have actually simulated it on his own, sitting with his laptop or his computer at home, not talking to any prover. He could have come up with a simulated view. So this is again a probability distribution. He can essentially sample these simulated views himself. And what has to be true about the simulated view in terms of relation to the real view is that if there's someone else out there, like let's call him the polynomial time distinguisher, and he's pressing a button saying, give me a sample in the distribution that you have. I'm trying to determine whether I'm talking to the real view or I'm talking to the simulated view. I'm just going to keep pressing the button, getting views. And at the end, I should tell whether all the views I got were from the real view or all the views I got from the simulated view.
Okay, I want to deliberate on this because I think this idea of distinguishing is very, very important on its own. So I want to give maybe a more isolated example. Maybe we want to see it outside of the context of zero knowledge, just to see something a bit simpler. So I want to tell you a bit about pseudo-randomness. So, so we have this thing called a pseudo-random generator. It's a circuit that is given like say 100 bits and outputs 200 bits. But it has the following property. If okay, let's just give some notation. Okay, is a circuit, let's call the circuit G, that is given, say, a 100-bit string X and outputs a 200-bit string, which we will call G of X. Okay, so it has it with the following property. If X, you know what, I'm gonna change it from X to R because it's common to call it R for random. If R is uniformly random, then GR seems random. So what does this mean? So first of all, notice that there are 2 to the 100 strings of length 100 and 2 to the 200 strings of length 200. Okay, so the latter is much larger, right? For any string of length 100, there are 200, 2 to the 100, which you can check is a lot, strings of length 200, right? Because I can complete it in 2 to the 100 different ways. So this is much larger than this. Like 2 to the 200 should be something like 10 to the 106, I think the relation is. No, it doesn't make sense. It should be like 10 to the 80 or something like this, like a number with 80 digits. So this is just the ratio between these two. But G is deterministic. So if there are 2 to the 100 strings R, there are 2 to the 100 strings GR. So this means that if I sample a random string of length 100 and then apply this string to it, no matter how this works, I'm only going to be able to get a very, very tiny fraction of all the strings here, right? So it's, for every string that I can get this way, there are 2 to the 100 strings that I can, minus 1, that I cannot get in there. So it's a very, very tiny, negligibly small fraction. Yet, somehow, we want to say this, even though these distributions look very, very different, because a uniform, a random string of length 200 gives every string the same probability, whereas if I choose this random string R and they apply this pseudo-random generator magic thing, I'm going to get something, one of a very, very small set of numbers. It is impossible to tell the two options together. So what does this mean? Again, so how can these distributions be the same? Okay, I'm just gonna add here. I'm gonna make this PDF available, by the way, this document. So GR is very concentrated. So how can these distributions be the same? So the idea, choose, consider someone whose job is to distinguish the two. That is, he is given many, he can, okay, how am I going to say it? So I have two boxes, okay? I have the box, let's call it B0, that has a button that whenever you push it, the box samples R of length 100 and outputs GR. So this box only needs 100 bits of randomness, and then it applies this generator. And B1 that has a button that whenever you push it, the box samples R of length 200 and outputs it. So this is a box that represents the first situation, where the pseudo-random situation. So it's pseudo because it only has 100 bits of randomness, but it's trying to pretend to have 200 bits of randomness. And this second box is the truly random. A distinguisher is given the box BB, where B is a random bit. So I'll just, the way we denote it is like this. B gets uniformly at random either 0 or 1, and has to guess B. B, the small b. He has to guess what box he was given. Okay? So we say that B0 and B1 are computationally indistinguishable if for any efficient distinguisher, well, if the distinguisher just outputs a random B, he says, oh, it's the left box, but he's just guessing, then you will be correct with a probability of half. Now, what we want to say that it's like you can do much better than this. The probability that they guess correctly is very close to 1/2. So it essentially means that no matter what you do, as long as it's efficient, it would behave exactly the same way here or here. Because if there is like a noticeable, tangible difference between using this distribution and using this distribution, then you could have used this difference to distinguish between the two. So essentially this means that for all intents and purposes, if you use this box, you can pretend that you've used this box, because again, if there are differences, then you could use them to distinguish them. And this is the meaning of pseudo-randomness. You can be very, very, very far away from randomness, very different from randomness, extremely highly concentrated, but for anyone efficient, you will have to, they could not tell the difference. Surprisingly, this is a relation to black holes, but I'm going to talk about it in a different opportunity. So what Shafi was talking about is similar, but she looks at more complicated distributions. I said, okay, you have like this pseudo-random distribution and the random distribution, and you can tell them apart. And she says, okay, you have the distribution of real transcripts that could have occurred by communicating with the verifier. But I also can code a simulation. It doesn't even interact with the verifier. It just like makes up conversations on the spot. But if I give you 1,000 conversations that are real, and I give you 1,000 conversations that I sampled from the simulation, or 1,000,000 or 10 millions or any polynomial number, that wouldn't be enough for you to tell which one I gave it to you from. So this essentially means there is no information that could be efficiently computed from here that cannot be computed from here, because otherwise, again, I could use this information to distinguish them. But the beauty is that anything that can be computed from here, I essentially can compute myself, because this is a simulation that I wrote, the verifier. So this is why this definition, even though it's a bit involved, a bit complex, it captures very well the meaning of the actual conversation is inconsequential. It doesn't tell me anything except the completeness and soundness that are guaranteed by the protocol.
If a distinguisher can't tell this apart, can't tell better than essentially 50-50, I say that these two views are computationally indistinguishable. He just, a polynomial time distinguisher cannot tell them apart. Let's chew into this a little bit further. What does it mean that two probability distributions are computationally distinguishable? In our case here, the two distributions are the real views and the simulated views, but it doesn't have to be applicable to this particular setting. We can talk about computational distinguishability as a notion more generally, where again, there are two distributions. In our case, there were views, but there could be just two k-bit strings. And the game is that there's a distinguisher on the other side of the wall, and he can press a button and get samples, always from either all the samples from distribution D1 or all the samples from distribution D2. And his wish is to distinguish which is the case. We say that these two distributions are computationally indistinguishable if for whatever strategy this polynomial time distinguisher employs, so for all distinguisher algorithms, even after receiving a polynomial number of samples from the distribution sub either 1 or 2, the probability that he can guess whether this was distribution 1 or distribution 2 is less than a half, less negligible. Negligible in what? There's some sort of security parameter, which I call K here, which might be the size of the strings of the samples, the size of the sample string. So back to zero knowledge. Here's a definition. An interactive protocol, PNV, is zero knowledge for language L if there exists a simulator, an algorithm, SIM, such that for every x in L, so I'm only requiring it when the theorem is correct, only when x is in L. And why? Because you do get something, you get that x is in L. That's a detail aside. So I require that the following two probability distribution are polynomial time indistinguishable. The first is the real view that the verifier gets during an interaction. The second is an output of the simulator. The simulator here is taking x as an input, just the x. He doesn't have any square root of y or any secrets, just the input that both P and V see. You notice here that there's another input to the simulator, which is this 1 to the power lambda. This is essentially a technicality. It's because we want to make sure that we allow the simulator to run enough time, polynomial time, and sometimes when x is really small, that doesn't give him enough time. But really, for all practical purposes, if we're thinking about large x's, forget about this one. So both of them, the simulator runs in polynomial time. To be zero knowledge means that these two distributions should be computationally distinguishable, and that will make a protocol, PV, a zero knowledge interactive proof if it's complete, if it's sound, so it satisfies completeness and soundness, and it's zero knowledge according to this definition. Almost. Two caveats. We're going to let this sim guy, this probabilistic polynomial time, run in expected polynomial time. What that means is that the simulator might expected polynomial time essentially means that if you take the expectation of how much time the simulator runs over all possible randomness of the simulator, it's going to be a polynomial time. What essentially that means is that there might be some very, very unlucky coins for the simulator, which will take him a long time to run. But typically, he's going to run in polynomial time. This is something that you guys should know, and that is the definition of expected polynomial time.
Well, don't worry too much about what expectation is, but you will see the technicality, why this technicality is important, I guess, soon. The thing is that we are going to use a technique called rewinding to create the simulation. So the point of the technique is that we are going to ask a question, and then, or what we are going to do is that we are going to start from the answer and work back to the question. This is like the nice thing is if the question is random, then the answer could also be random. So if we want to simulate a transcript where I give you an S and then I give you the square root of S, then when you ask me, then instead of what I can do is I can choose in advance the square root. We'll see. The point is that if it's hard to compute the answer but easy to compute the question, then what I can do is to choose a random answer and then compute the question, and I know the answer because I chose it, not because I have some magic ability to solve the hard problem. Like, we are trying to show a simulator for, I don't know, proving that I know a signature key for something, then I could choose the signature key myself, and then obviously I know it. I hope that we're going to see an example of such thing. And I think after we finish with the simulation, we'll be done for today. It's going to be a two-parter because it's longer than I thought it would be.
One more caveat. In this definition, I never said anything about the verifier. I just said that a particular pair of P and V is zero knowledge if the following conditions hold. But we want this to hold really the zero knowledge property for every verifier, even a cheating verifier. So the real final definition has to take into account the possibility that the verifier might be a liar and might be trying to get knowledge when he shouldn't. So he's not honest. So we finally get the definition that a protocol is zero knowledge for language L if for every V star working with P, okay, there exists a polynomial time simulator such that the view and the simulation are computationally indistinguishable. And I'm using this squiggly equality to mean computationally indistinguishable.
Yeah, there is a small mistake in this slide. It should have been V star here. Not here. Here it is a PV because that's the label of the protocol. But here it's V star. And it's important that V star is different than V because when we specify a protocol, we say how people should behave if they are honest. The view of V star of PV, the reason we will put the star here and not here is to emphasize that this V star behaves differently than how we expected it to behave, which is V. And the point is that no matter how V star behaves, to say that it's zero knowledge, you say that no matter how zero star behaves, we could simulate the conversation not just with an honest verifier, but with any verifier. And no matter what it is, as long as it's PPT, PPT means probabilistic polynomial time, which essentially means it's efficient, but it's allowed to flip coins. And so no matter what it looks like, no matter what it does, no matter how it behaves, we can simulate the transcripts as before, which means as before that they can't actually learn anything new from these transcripts because everything they can do with these transcripts, they can also do with the simulation that they can run themselves.
Might be different probability distribution, but the distinguisher cannot tell them apart. All right, so let's rest a second. So PV is zero knowledge if for every V star there was, no matter what V star does, actually we could have simulated this in our own. Why does this capture the intuition that what the VAR can learn during the interaction doesn't add any computational power? Remember, our original intuition was that what you can compute before and what you can compute after is the same. The reason is because we say the following: listen, maybe there is a V star, really devious one, who can get something out of the prover. Being zero knowledge says no. If such a V star exists, then we could have computed this before, because the simulator could use that V star to come up with a simulated distribution, which is more than what the view is. But the zero knowledge requirement says that that's not possible. That for every V star, there will be a simulator that can achieve the same distribution, essentially, computationally equivalent to what can happen in the real view. And therefore, the real view did not add any computational power. All right. By the way, this is what's called a computation indistinguishable zero knowledge. Sometimes people use the notation ZK, C for computational. But there are other flavors of zero knowledge. You can also ask for a perfect zero knowledge definition. So where the real distribution and the simulated distribution are identical, or maybe statistically close. So a perfect zero knowledge is a special case when if you look at the view of the verifier, and then we can actually simulate it perfectly. So the simulated view and the real view are the same, and that means that they're indistinguishable for any algorithm. So this would mean that when you can prove perfect zero knowledge, it's an unconditional result. Because usually when we only prove computationally zero knowledge, we make some assumption that there are some computations which are hard. Whereas with perfect, it's just perfect zero knowledge. There's no difference between what we can learn during the view, during the real interaction, and what we can learn from a simulation. Let's work through a simulation now that we have a definition. Recall the protocol for quadratic residues. So the prover sent R squared, he asked for either seeing R or R times square root of Y, he got back an answer, he checked it. So what's the view here? The view is S, that's the first message, B, second message, and Z, third message. And what are the coin tosses are B, so it's anyway included. It's SBZ. How do we simulate that? Well, we're going to simulate this a little bit in a different order afterward.
So here is the thing. Say I am the verifier and want to simulate what something that looks like I talk to the prover. So one thing that I can do is to sample an S and then flip a coin. And And if the coin is 0, then I output R, right? Because I know that S is R squared. But what do I do if I get 1? I don't know how to compute the square root of this. Why? Because I know how to compute the square root of this. So if I can compute both, right? I'm sorry, I meant I don't know how to compute the square root of S times X squared of this. I don't know how to do this both when B is equal 0 and equal 1. I know to do it when B is equal 0. Y to the 0 is just 1. B is equal 0 means that Y is not there, just Z squared equals S. And okay, I do know how to solve this because I chose R. But I can't solve this also for S times Y. Why? Because if I could have done this, then I could take the square root of S times Y, divide it by the square root of S, which I know this is just R, and get back the square root of Y, which is exactly the thing I don't know how to compute. This entire discussion relies on the assumption that it's too hard to compute for myself, and this is why I even need the verifier. So how would I do the simulation? And I don't know what Shafi is going to say, but my guess would be that what I'm going to do is I'm going to choose some random number, and then I'm going to look at Y over this number. Let's see.
The simulator can't just choose an R and send himself a message. I mean, he could, but then if you toss a coin, so you only know how to return R. You don't know how to return R times square root of Y. So how are we going to get a simulation? The idea is as follows. And we're going to show a simulator just for an honest verifier. And in fact, the simulation is going to be a perfect zero-knowledge simulation.
Mm-hmm.
What the simulator is going to do is, rather than really go in the order that
So instead of choosing S truly randomly, I'm choosing it in a way which is convenient for me. But the thing is that it still is uniformly random. Just I have different information about it. So I can choose S to be R squared always, right? But if I take a random number and then divide it by Y, it's still a random number, right? Because this division by Y is like, it's called an automorphism. Just if I take in this clock arithmetic world, in this modulo arithmetic world, if I take a random number, uniformly random number, and divide it by any number, it doesn't have to be uniformly random. It could be fixed. It could be a known Y. Then I still get a uniformly random number. So this is why it's not a problem that I choose S this way, but choosing S this way allows me to answer both questions.
Real interaction is that he's first going to choose the question of the verifier. And he's going to do that just the way an honest verifier would do. He picks a random bit B. Then he's going to actually pick the third answer, which is he's going to pick a random Z. Notice that Z actually is just a random number, except in this case it's R, in this case it's R times X. So the only thing that remains is to make sure that I can figure out for which S would have been Z the right answer. And note that this equation, S equal to Z squared over Y to the B, mod n, satisfies exactly what S should be. Why is that? Let's look at this. Let's plug in B equal to 0, in which case S is equal to Z squared. That's exactly what it should be. In the case that B is equal to 0, Z is the square root of S. What about when when B is equal to 1? Then I'm letting S to be Z squared over Y. Is that correct? Let's think about it. If you look at Z here, it's supposed to be, in the case of B equal to 1, R times X. And what's the relation of R times X to S? The relation is that if I square this, I should get S times Y. And that's exactly the case here. If I square Z, I get S times Y.
I really strongly, highly, emphatically recommend that each of you gets a piece of paper and writes the details down. The math is not hard. You can even like put it in the comment and I'll tell you if you got it right. It's not hard to work out, and it's a really nice exercise in zero knowledge. I think getting this down will go a very long way in becoming more comfortable with the concepts and notions here, because it's an example which is simple enough to throw on you, but deep enough and complicated enough to have interesting phenomena that are non-trivial and are really quite surprising and striking.
So, lo and behold, I was able to come out with a triplet, which is identically distributed as what the view of the verifier, the honest verifier, is during an interaction. Obviously, this doesn't convince me of anything. It's not that I actually got an R squared and then I asked a random B and got the response. I did this in my basement in a simulation. But the view is identical. Now, what about when the verifier is not honest? So what about the case, the general case, where the verifier might not be tossing a coin and sending over? That's a little bit of a problem. What if this, adversarial verifier was the kind that when he saw some S, he did some very complicated function or computation on S, and depending on the result of his computation, would ask a particular B. Then he might have gotten something interesting depending on his computation. Well, I will show you that even if he was an adversarial, very complex computation, I could still get the same view that he did using a simulator. How is that? Again, I will pick a random B, even though he doesn't select things at random. But wait, I'm not done yet. I pick a random B, then I pick a random Z, and now is when I do something different. I say to myself, all right, I will, for a minute, suppose that indeed B would have been what he will ask me, the bad guy, the adversarial guy. And I will compute S accordingly. And now I will actually send S to this bad guy. What does it mean, send? Remember, the simulator should work correctly for every V star, for every bad guy V star. The simulator has access to V star. The intuition is that no matter how...
Yeah, this is something that is easy to miss or misunderstand. When we simulate V star, we can use it. Like we know how V star works, and we can communicate with it as though we are doing the actual protocol. It's not really a protocol because we do it all locally. We just run the code of V star and like kind of pretend that we are a verifier, but everything is happening locally. There is no interaction or protocol for real here.
Powerful the verifier is his polynomial time, and I have to come up with a polynomial time simulator. So a polynomial time program can have access to any other polynomial time program, including this verifier. So what I do is I run this verifier, the bad verifier, on the input ny and first message s, and see what he asks for. If I was lucky, he's going to ask exactly the bit that I prepared for, and I know how to answer. But he might not do that. In which case, I can't really output S, B, Z because I just don't know the correct answers. What do I do then? I start again. I go to step one, I again pick a random bit, I again pick a random Z, I then compute S, and now I ask V star on this new N, Y, and S.
So this is what I described as rewinding. And because we control the entire thing, it's not an actual protocol, it's just a simulation. And we could always, as part of the transcript that we're writing, we could probe the V star in the many different ways. We could take it back and ask them to run again, and they will choose new randomness. We can do all sorts of stuff. Interestingly, one of the reasons that quantum cryptography is very hard is that you can't rewind, because one of the operations in a quantum setting is that you measure the state and it collapses. And this kind of action is irreversible. You can't go back from it. The laws of the universe do not allow it. Once you measured, then the rest of the information of the state that you didn't get from your measurement is lost forever. And so it's kind of interesting to note that this rewinding that we take for granted is actually, as in the quantum setting, it doesn't exist, and it makes things, I wouldn't say it doesn't exist. There are quantum rewinding techniques, but they aren't as general as this. You can't always say, oh, we'll just rewind it, and it causes a lot of problems. So after having done my DD in the world of quantum cryptography, I appreciate the ability to always rewind very, very much.
Why am I hoping that this time it's going to be better? I don't know if this time it's going to be better, but I do know that whatever it is that V-star is doing, this is a fixed behavior, but my B was chosen at random. What's the probability that a random bit will equal a fixed behavior? 50-50. And that means that within 2 trials, I will be lucky enough to hit on the question the V-star would have asked.
Yeah, if an experiment has like a probability P of succeeding, then you would need about 1 over P attempts. And if you roll a die until you get a 6, then on average it's going to take you 6 rolls. And when I say on average, I mean that if you repeat this many times and for each time you count how many attempts it took, and then you take the average overall attempts, you will see that as you do more attempts, and you are welcome to do this at home, this experiment, math experiment, you will see that the average converges quite fast to 1/6. And actually, in the appendix of the new version of my book, which will be uploaded soon, I prove this in the appendix. So if you want to know why this is true, there is a nice explanation.
I suggest that you think about this more deeply and prove to yourself that the expected number of repetitions is 2 before I can output a triplet SBZ. And this is why we require the simulator to be expected polynomial time. So within expected 2 trials, I will be able to output something that is exactly the same distribution as would have happened in the real interaction. All right. I want to say that actually, if you think about this a little bit deeper, you realize that not only the prover convinced the verifier that
going into the definition of a proof of knowledge is an entire new can of worms that I don't think we should get into right now. I think now is a good time to stop. I think that what I'm gonna do is upload it and then discuss with you guys on X on the schedule, and if there is like an interest, we'll set up a fixed time. I think it's gonna be like a weekly thing, like every week at a certain evening. We're gonna watch and go over as much as we can in like 2 hours, and then move on. Okay, so I think that's about it for this evening. And I would like to know in the comments how do you enjoy this experience, especially for those of you who don't have a lot of formal background. And if you think this is nice, if you'd like me to continue, please let me know. And thank you all for coming. Thank you. I really enjoyed myself. Much nicer watching this lecture when there are other people floating about, even if I think you could have made a bit more effort to ask some questions, be engaged, but I get it. It's highly theoretic, it's highly abstract for many people. It's kind of alien. Part of what I'm planning to do, by the way, is to start each meeting, except the first one, obviously, by a brief overview of what we've done last time. And so, in my experience, if you let stuff just hinder or hibernate in your brain for a week, even if you don't think that you thought about it during this time, when you reapproach it, you find that it is easier, that it sits better, and that yeah, someone is writing in the chat, Nacho. He's been sleeping next to me this entire time. I didn't want to bother him, but maybe he'll let me if I'm nice enough. Evil guy. Yeah, so really, I really recommend that after I upload it, you try watching it again, ask me questions, and I think it's gonna be a lot of fun. Also, if there are other talks, other lectures that you would want to watch together, just let me know. Okay, guys, I'm stopping the stream now. See ya.